Okay, Chapter 9 discusses chemical reactions. So, a chemical reaction is a process by which one or more substances are rearranged to form different substances. We looked at chemical reactions back in Chapter 3, and you saw the indicators that a chemical reaction takes place when we looked at the chemistry in a bag lab. So, we're going to revisit that stuff and we're going to look on a molecular level what is happening to atoms during a chemical reaction. All right, so what is the evidence that a chemical reaction has taken place? Things are change in temperature, color change, sometimes there's a smell or gases are released. And also, there's this one is on your slide, but not on this one. It's the formation of what's called a precipitate, which is a solid that forms during a chemical reaction. We need a way on paper to represent chemical equations, so we use these different symbols to show on paper what's going on the atomic level that we can't actually see. On the left-hand side of a chemical reaction, those are called the reactants on a chemical equation. And the right-hand side, the other side of the arrow, these are called the products. These are the substances that are formed during the reaction. So the table summarizes all the different symbols that are used for chemical equations. The plus, it separates the two reactants, so you have one reactant plus another reactant. The arrow means that two reactants or one reactant, whatever it may be, is producing some product, so it often stands for yields. And a double arrow going back and forth, this one right here, would represent a reversible reaction, which is deals with equilibrium. And then a little S in parentheses identifies the solid state of matter, L is liquid, G is gas, and AQ is aqueous. Aqueous is different than a liquid. A liquid is a pure substance like water or maybe ethanol, something like that. AQ means that something is dissolved in water. It's an aqueous solution. So if we're going to represent chemical equations in words, we would do it like this. We would say aluminum, and that means solid aluminum, plus bromine, which is a liquid, pure substance, yields aluminum bromide solid. So you can see that it's important what we learned last chapter, all those naming rules and everything. If you don't know your naming rules, you're not going to be able to name the reactants and products in a chemical reaction or write the formulas for those reactants and products. This is what's known as a skeleton equation, uses symbols and formulas to represent the reactants and products. So the skeleton equation is showing you that solid aluminum reacts with liquid bromine to produce aluminum bromide solid. What skeleton equations lack is information about how many atoms are involved in the reaction. So we won't actually be doing skeleton equations very often, but it's just an outline to get you prepared for what we will be doing. Okay, so what a chemical equation is it's a statement that uses chemical formulas to show the identities and the relative amounts of substances involved in a chemical reaction. So this is showing you that one aluminum atom reacts with two bromine atoms to produce aluminum bromide. And remember, bromine is one of the 7 diatomic molecules, so it's an atom that will never exist by itself. So bromine you'll never see just Br in a chemical equation. You'll see Br2. And remember, the other 7 are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the 7 diatomic molecules. Okay, so according to the law of conservation of matter, we need to have whatever appears as a reactant needs to be present as a product. So if we have 2 aluminums in the reactants, there have to be 2 aluminums present in the products because nothing disappears during a chemical reaction. It's just atoms are rearranged, they may combine in different ratios, but they don't disappear and they don't appear from nowhere. So if they're part of the reactant, they have to be present in the products, and it has to be the same quantity. So we represent that by balancing the equations. Coefficients are used to balance these equations. So you see that there are 2 aluminums, 3 bromines to yield 2 aluminum bromides. If we take a total count of the total number of aluminums on the reactant side, you'll see that there are 2. If we take a total count of the aluminums on the product side, you will see there are 2 also. So this coefficient applies to this element. This coefficient applies to this element. Now notice there's a subscript here. So we actually have 6 bromine atoms in this chemical formula. And then over here, we have 2 aluminums, and we have 2 times 3, we have 6 bromines. So we have the same amount of atoms on each side, equal amounts. So just like I said in the previous slide, a coefficient in a chemical equation is the number written in front of a reactant or product, describing the lowest whole number ratio of the amounts of all the reactants and products. You can't change subscripts. Once you've written a chemical formula correctly, you can't change the subscripts. Just like, let's say I have water, H2O. I can't change the subscript for water. I can't change the fact that there are 2 hydrogens and 1 oxygen, because if I did that, it would no longer be H2O. So if I have H2O, I can never change the subscript, or I change the identity. But what I can do is I can put a coefficient in front of the H2O to say, okay, I have 2 H2O molecules. So what I have here, what this is an abbreviation for, is saying I have an H2O and an H2O. If I count up the total number of atoms, 2 times 2 is 4, so I have 4 hydrogens, and I have 2 oxygens. So instead of writing them out like this, I can write it out like this using my coefficient to represent how many of those water molecules I have. So the point is here, you can never change the subscripts once a chemical formula is correctly written, because you change the identity of the substance, but you can put a coefficient in front of the chemical formula to change the quantity of that substance that you have. Here are some rules for and some steps for balancing equations. I gave you a slide that's enlarged at the end of your notes, because this ends up being pretty small on the slide, the handouts that I gave you. But this is how you balance chemical equations, and we're going to do a lot of practice with this in class. Step 1, you're going to write the skeleton equation for the reaction. So we have H2 plus Cl2 yields HCl in this example. And then you're going to count the atoms of the elements in the reactants. So at this point, we have 2 hydrogen and we have 2 atoms of chlorine. Then step 3, we're going to count the atoms of the elements in the products. So over here on the products, we see that we have 2 atoms of hydrogen and 2 atoms of chlorine. And then step 4, you will change the coefficients to make the number of atoms of each element equal on both sides of the equation. You're never going to change a subscript in a chemical formula to balance an equation, because doing so changes the identity of the substance, as I had mentioned earlier. So let's practice with the previous example that was given to us, which is this. Let's say I have aluminum plus bromine, and it yields aluminum bromide. And let's not worry right this second about how I figured that out, how I knew aluminum and bromine came together to form aluminum bromide. We'll learn that when we learn chemical reactions. I want to focus right now on just being able to balance these chemical equations, so getting equal numbers of atoms on both sides of the equation. All right, so I'm going to put a little line here to represent where the coefficient will go. And I start taking account of atoms. My suggestion is, if you ever have oxygen, if you ever encounter oxygen, do not balance oxygen first, and don't balance hydrogen first, because it makes it a lot more difficult. Balance metals first, then balance nonmetals, then balance oxygen and hydrogen last, and you'll see that it usually falls into place. We'll talk about polyatomic ions and balancing those here in just a minute. All right, so I have one aluminum on each side. So for right now, that's balanced. But over here, I have two bromines and I have three bromines on the product side. So the only thing I can do here is if I put a 2 here and a 3 here, that gives me 6 bromines on each side. All right, that's the only way I'm going to get an equal number of bromines on each side is to put that coefficient. Well, now what that does is it changed the number of aluminums that I have. So you notice now I've changed the coefficient here. So instead of having one aluminum, I have two. So I need to go to this side and put a 2 in front of here. So what this is saying is I have two aluminums reacting with three bromines to yield two aluminum bromides. That's the process that you need to go through. It's a little bit of trial and error, but once you get the hang of it, it becomes easier and easier to balance these equations. All right, so this is just a summary of the last two steps, making sure to check your work, making sure you have a correct ratio of all the atoms and that you have equal numbers of all atoms on both sides of the equation. So reactants and products. All right. What this represents is the most fundamental law in chemistry, which is called the law of conservation of mass. We've discussed it before. Balanced equations show this law. So again, we can't create matter. We're not destroying matter. Matter is conserved. So what you start with as a reactant has to be present as a product. So this is a little flow chart here. It may help you, it may not help you to balance equations. A lot of it, again, is trial and error.